This video is about using standard enthalpies of formation to figure out how much energy change there is for a reaction. So this is very similar to when we talked about Hess's law. This is just going to be another way that we can use to figure out what is the total amount of energy or heat change in a reaction. Okay, and so one thing we need to remember is that all chemical reactions involve starting substances that get broken apart and made into new substances. And how we do that is we have to break apart the bonds that hold each reactant molecule, and then we form new bonds. So for instance, in this diagram here, we've got methane and oxygen. Well, if you look here, this carbon is the black dot. That's connected to hydrogen. But in the products, it's connected somewhere else. Well, how do we make that happen? Well, first, we have to break apart this little party here. We have to break apart these bonds. And so the first step of any chemical reaction is breaking apart the bonds of the reactants. And then the second step of a chemical reaction is making new bonds for my products. So not only do we break apart carbon and hydrogen, but then we also go ahead and we reform carbon with oxygen. Okay? And that's important to make sense of why we're doing what we're doing with standard enthalpies of formation. Because what happens is that when you need to break apart a bond, you have to put energy into it. So if you think about you're playing with Legos, we talked about Legos in the Hess's Law video. When you're breaking apart Legos, you have to put energy into it. Okay, so when you're breaking apart bonds, you put energy in. And then the opposite happens when you make bonds. When you make bonds, you release energy in that process. So all reactions, whether they give off or take in energy, ultimately comes down to how much energy did we put in to break apart the bonds that were there initially, and then how much energy was given off when we made our new bonds. And this is going to be a really helpful way to understand why we do what we do with standard enthalpies of formation. Okay, and so like our objective said, we're going to come up with, for a reaction, what is the amount of energy being lost or gained, and all based upon enthalpies of formation. So what this is saying is if I know the amount of energy that it takes to break bonds, and I also know the amount of energy it takes the amount of energy that's released when I make new bonds, I can use those two numbers to figure out the overall change. So for example, if in this made-up situation, if it takes 100 kilojoules of energy absorbed to break apart these bonds, and then when it makes new bonds, if it releases, let's say, 50 kilojoules of energy, well, we can compare those numbers to figure out what's the overall change. Well, I had to take in 100 for the first part, and then the second part, I released 50. So what's my overall change in enthalpy? It would be 50 kilojoules, right? Because used 100, I got rid of 50 again, so that means I have 50 remaining. This is what we're doing here. And so we can do this with any reaction if we know the standard enthalpies of formation. And I've mentioned that a bunch here, but what that is, enthalpy just meaning heat, formation meaning making something. So it just stands for how much energy is involved when you make 1 mole of a substance. Okay? And there's tables that list out all of these for most elements that you'll work with. And here's just a sample of 4 different ones. So what this is saying is that if I'm making hydrogen sulfide, there's 21 kilojoules of energy that are given off. This is how it's made, but this is the amount of energy that's given off. And then same with hydrogen fluoride. I make it, and then in the process of making it, there's 273 kilojoules of energy given off. Well, if you think back to what we talked about with Hess's law, what if I start with this and then break it apart? Basically, I'd be flipping this reaction. Well, when we said when we flip a reaction, that means we flip the sign. So what this means then is that if I'm breaking apart the bond, so if I start with hydrogen sulfide and I'm actually needing to break it apart so I can put the hydrogen and sulfur somewhere else, that I have to put in 21 kilojoules of energy for every mole. And then for hydrogen fluoride, if I want to break apart the hydrogen and fluorine, I have to put in 273 kilojoules of energy. Okay. All right, so let's look at this example. So here we've got hydrogen sulfide and fluorine, and these, remember we said, are going to get broken apart to make these two new products. Okay, so remember the first part, like we said, is going to break apart these bonds, and there's some amount of energy. There's some amount of energy that's going to be absorbed to make that happen. And then the second part is going to be when we make new bonds. So we broke apart all of these molecules, and now we're going to reassemble these into new things. So now I'm going to combine hydrogen and fluorine. And when I do that, there's a certain amount of energy that gets released. And when I combine sulfur and 6-fluorine together, there's a certain amount of energy that gets released. Okay, so if I know those amounts of energy, I can figure out what's the change in enthalpy for the entire reaction. And so we can do that if we have a chart like this, which will be given. There's one in our textbook we'll see in just a second. All right, so looking at these values, hydrogen sulfide, when I break apart the bonds, I have to take in 21 kilojoules of energy for every mole. Well, moles, remember, are the numbers in front. There's not a number there, so we assume it's a 1. So there's just 1 mole of this that I'm breaking apart. So that's going to involve how much energy? It's going to involve 21 kilojoules of energy. Hydrogen fluoride. When I make hydrogen fluoride, I know I'm making hydrogen fluoride because it's in the products. I can see in my table that making hydrogen fluoride involves a releasing of 273 kilojoules of energy. And then sulfur hexafluoride, looking at our table, the bottom one, we see that there's a release of 1,220 kilojoules of energy. Okay? And then one thing that's worth noting, we don't see anything about fluorine, but any diatomic element, so Hofbrinkel, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine, those almost always are actually, there's no change in energy when we make those. So that's why I have a 0 here. I could look that up on a table and find that value, but just trust me that that's why it's 0. And so I figure out that there are 21 kilojoules that are required to break apart the bonds of the reactant molecules. That's this part here. And then I find that there are negative 1,766 kilojoules. The negative just means they're released when I make the products. So those numbers, again, come from this. This is something that's been observed and measured for making these compounds. Now, why do you think, and here's my overall answer, so then I would just combine them, right? 21 gets absorbed, but negative 1,766 gets kicked off. So I combine these to get my total change of enthalpy for the reaction would be negative 1,745 kilojoules. Now there's something that I did that I haven't talked about yet, and that's this here. I multiplied by 2. But why did I multiply by 2? Well, if we look here, this is how many kilojoules are given off for 1 mole, right? But in the equation, I don't just form 1 mole of hydrogen fluoride. I actually form 2 moles of hydrogen fluoride. And so to figure out the amount of energy for 2 moles, I multiply this value, this formation value, by 2. So that's why I did that. If there had been a 4 in front of sulfur hexafluoride, I would take this number and I'd multiply it by 4. And that would tell me how much energy was involved with making 4 moles of that compound. Okay? So we can think of every problem like that. Or basically doing this process simplifies into a reaction such as this, where if I want to know the change in enthalpy for a reaction, I take the total of the formation values for all the products, and then I subtract the formation values, heat of formation for all of the reactants. Okay, when I do it this way, I don't have to keep track of whether or not I need to flip signs. I can just look at the values from a table and just plug them in. I add up all of the products together, and then I subtract the sum of all of the reactants. So we're going to actually look at 2 examples, and one is the example we just did. So here, we just did this one before, but if I'm using this equation to find the change of enthalpy for the reaction, I'm going to take the sum of all of my heat of formation values for the products. I didn't copy that table where I got these numbers from onto the slide for some reason. I forgot maybe to do that. Oops. Okay. But these numbers I look up. And so the amount of energy involved with making 1 mole of hydrogen fluoride was negative 273 kilojoules. But again, I actually have 2 moles, so I'm going to multiply that by this number by 2. And then the amount of energy involved with making sulfur hexafluoride is negative 1,220 kilojoules. So I'm going to add those up to get negative 1,766. And then I'm going to subtract whatever I get when I add up the values for my reactants. I look in the table and I find that to make hydrogen sulfide, dihydrogen sulfide, I release 21 kilojoules. And we talked before that fluorine is 0 kilojoules. So I combine those to get negative 21. So I get negative 1,766 kilojoules minus a negative 21, which your math, minus a minus is plus a plus. So we end up adding them, and I get negative 1,745 kilojoules, which was the exact same answer I had just gotten. Okay, so I've mentioned about there's tables for values. So this is something in your textbook. I think it's around page 895, but there's a listing of all of these different compounds and the amount of energy it takes to make that. And so this is a table I would use. Instead of maybe using Hess's law, I could use this table to help me figure out how much energy change there is for a reaction. Okay, so let's look at one last one. I think my face is maybe covering this up a little bit. I'll move that. See, here are 2 heat of formation values. So to make nitrogen, dinitrogen tetrahydride, I absorb 51.6 kilojoules for every mole, and to make water, there's a release of 285.9 kilojoules for every mole. So here's my equation. Right? So I'm going to use this. Here's my chemical equation. I'm going to use this equation to figure out what's my change in enthalpy for the reaction. So my products are nitrogen and water. So I know I release 285.9 kilojoules for every mole of water. There's 2 moles, so I multiply that. Nitrogen is one of those diatomic molecules, so it has 0 kilojoules. I could look that up on a table. Dinitrogen tetrahydride absorbs 50.6 kilojoules per mole. Oxygen, there's 0 kilojoules when it's formed. And then I combine these, so this ends up being negative 571.8 when I multiply those, plus 0. And then I subtract 50.6. And I get the total change in enthalpy for that reaction is negative 622.4. So that is how we use and why we use standard enthalpy of formation to find the change in enthalpy for a reaction.